Okay, this is sort of the later section of chapter 18. It's about uneven covalent bonds, which form polar molecules. So when two atoms are the same and they experience a covalent bond, the distribution of electrons looks something like this. You'll usually find electrons in between the atoms, but sometimes you can find them out here, sometimes you can find them out here. Electrons are really weird. It's hard to pin down where they are. All you can really do is describe regions in space where it's most likely that they are. So in a covalent atom covalent molecule like this, it's likely that the electrons are found in the middle. But they could be over here and they could be over here, and this region looks kind of like a peanut and it's symmetrical. So this is called a non-polar molecule. Non-polar. I think I'm jumping the gun. I think this is on the next page. Yeah, we'll get there. But if hydrogen bonds to something else that's not hydrogen, it's really unlikely that the distribution looks exactly the same on both sides. So when hydrogen bonds to fluorine, still you're going to have this region in the middle where usually that's where the electrons will be found. But you'll have a small lobe right here and then a big lobe right here. So this is uneven, or not symmetrical, and therefore it's called a polar molecule. And polar is a word that describes a thing that has two poles that are different from each other. Like the Earth has a north pole and a south pole. Magnetic fields are polar because there's two sides that are different from each other. In molecules, when you say a molecule is polar, it means the electrons can spend more time around one atom than the other atom. The actual separation of charge itself is called a dipole. The molecule can be described as polar, but if you're talking specifically about the charge separation, that's called a dipole. And a dipole is just a thing that has two poles. I know it sounds like I'm using two words to describe the same thing, but a dipole can describe anything with charge. So anything that has a charge separation, you describe that charge separation as a dipole. It's got two poles now. The notation and symbols used to describe dipole is right here. It looks like a music note kind of, and to draw it you do like this. This is the lowercase delta. Lowercase Greek letter delta. Uppercase delta was a big triangle. Lowercase delta looks like this. It's kind of like a 8 that you don't finish drawing. Like, instead you do this. Okay, and you can label the sides of a molecule. The side that has less electrons around it is called the delta plus side, or the partial positive side, and the side that has more electrons typically around it you call the delta minus, or the partial negative side. It's not as extreme as an ionic bond. It's not like the electrons are always around fluorine and never around hydrogen. So that's why it's called partial. It's still a covalent bond. They still spend time with both atoms, but there's a favoring of the fluorine atom here. So that's the partial negative side. That's the partial positive side. This bond is described as a polar bond because it's uneven. It's not symmetrical. When electrons spend equal amounts of time around the atoms in a molecule, it's called nonpolar, which I said on the last page. Okay, one way to predict when molecules will be polar or nonpolar is to look at a property of the atoms that are making up the molecules. That property is called electronegativity, and we saw it before in a previous chapter, but electronegativity is basically a measure of how strongly an atom pulls electrons towards it. So fluorine is usually thought of as the greediest atom. It's got the highest electronegativity of everything else. And francium is on the bottom left. It's got one of the lowest electronegativities of all the other atoms. Those are kind of the two extremes. Typically the numbers increase as you go to the right and as you go up. So up and to the right, you have an increasing electronegativity. So if you look at the numbers, they're larger over here on the right side and they're smaller over here on the left side. So when things are really far apart, like fluorine and let's say cesium, that's going to be a super, super large charge separation. So large that actually those two atoms would be an ionic bond. That wouldn't even be covalent. Hydrogen is pretty low, and that's the only thing on this side of the table that really participates. That's the only metal that you usually find in a covalent bond, and hydrogen is not really even a metal. So, boron kind of has a smaller one than hydrogen, silicon has a smaller one, but around 2-ish is the lowest that it gets in things that form molecules and covalent bonds. The larger the difference between the two electronegativities, the more polar that will be. So if you look at this diagram, they're showing you that when an atom bonds to itself covalently, there is no electronegativity difference between them. So if you look up carbon's electronegativity, it's 2.55. So, and you try to find the difference, so 2.55 minus 2.55, that's where they got 0 from. There's no difference in electronegativity, so it's not polar. Electrons spin the same, its distribution of electrons would look very symmetrical. Well, that's what the shapes right here represent, the symmetrical distribution. Carbon and nitrogen, they're not too far apart from each other. If you look at the table, they're right next to each other, but there is a difference. 3.04 minus 2.55. 3.04 minus 2.55, that's where they got 0.49 from. So it's not huge, but there is a slight difference. The electrons typically spend more time around the nitrogen atom, so it's got a partial negative charge. Since they spend more time around the nitrogen atom, that means the carbon atom will have a partial positive charge. This little arrow is the symbol used to represent the strength of the dipole. It looks like this. The larger the arrow, the larger the dipole. And remember, dipole is just another way of describing how much the charge is separated from each other. Carbon and oxygen is a little farther apart. Carbon and oxygen are a little farther apart than carbon and nitrogen, so it's a little bit more polar than carbon and nitrogen. Its dipole is a little bit stronger, so this arrow is a little bit longer than that one. Carbon and fluorine is farther apart than any of these, so it's the strongest out of the ones on this page. And so therefore its dipole is the largest. What controls the polarity of each of these molecules? I think we said that already. It's the electronegativity difference. Why are some more polar than others? The difference is larger for some. Or you could say they're farther apart on the periodic table. Why is carbon bonded with carbon nonpolar? Because the difference, the electronegativity difference, is 0 because they're the same atom. That thing's crashing. Okay, difference is 0. All right, this is a figure from the textbook, kind of showing that ionic bonds and covalent bonds sort of form a spectrum of how far or how extreme the separation of charge is. An ionic bond is the most extreme separation of charge because it never spends any time around one atom, and the electron always spends time around the other atom. A polar covalent bond is similar to an ionic bond because there is a separation of charge, but it's not as strong. And a nonpolar bond is there's no separation between them at all. So we've been talking about molecules being polar and nonpolar, or no, we've been talking about bonds actually being polar and nonpolar. I'm sorry, I may have been saying molecules a lot back here. But if a molecule has a polar bond, it usually means that the molecule itself is polar. So if the bond is polar, the molecule is probably polar. But there are exceptions. So carbon dioxide looks like this. Each of the carbon and oxygen bonds themselves are polar. So there's a dipole pointing to the right, there's a dipole pointing to the left. Both bonds are polar, but because they counter each other and they point in opposite directions, the molecule itself overall is nonpolar. And this is something that's pretty hard to predict until you get more practice drawing the shapes of molecules and figuring out why they have certain shapes. But usually, if a bond is polar, the molecule will be polar. However, when more than one bond is polar and they cancel each other out perfectly, then you can get a molecule to have an equal distribution of charge everywhere, just because the nonpolar bonds cancel each other out. The fact that some molecules are polar means that is one way that those molecules stick to other molecules. We're about to see some ways where the different ways that molecules attract each other. One way is when nonpolar molecules are only weakly attracted to other nonpolar molecules. In these kinds of substances, because all the molecules in a balloon full of nitrogen are nonpolar, or a cup full of nitrogen, that material is not held together very strongly. So that typically means it has a low boiling point. It's easier to separate the molecules into a gas. Polar molecules, however, have a stronger force holding them to the other polar molecules that make up that substance, so they usually have slightly higher boiling points. And then ionic bonds would have the highest boiling point of all, because they are much more strongly attracted. When things have ionic bonds, like table salt, it's full of ionic bonds. That leads to a much stronger attraction in the substance, so it's pretty hard to boil table salt. It's like thousands of degrees. It's pretty high. However, for nitrogen, it's negative 196 Celsius, meaning anything below that temperature, it could be liquid, but anything above that temperature, it's going to be a gas, which is why you typically encounter nitrogen as a gas. Here's a chart showing some different boiling points. The ones on the top are all polar molecules, so even though we would probably think of negative 33 as a cold temperature, it's not as cold as these down here. And ammonia is polar, so it's got a higher boiling point than these down here. Water is really high. Water's quite polar. Hydrogen fluoride is 20 Celsius. It's like a chilly room. But these nonpolar molecules, substances made of these, all have really low boiling points. Water is polar. We drew a diagram earlier, I drew a diagram earlier that had a hydrogen and an oxygen and a hydrogen all in a line. And I said, we'll see how the shape's not really straight like this. It's actually bent. And some molecules they're called bent because they're bent, they're not straight. Some molecules do that because of these non-bonding pairs. Those non-bonding pairs actually find themselves up here pushing the two hydrogens down rather than being on separate sides of the oxygen like this. And that's not a thing, that's just a thing that has been discovered. It's not a thing that you would be able to predict yourself really until you get more experience seeing all the different shapes of molecules. That, because it's bent, if it were straight, the two dipoles would be pointing like this, and they would cancel out, like in CO2. CO2 is not bent, it is straight. But because it's bent, the two dipoles don't cancel each other out completely. In fact, they add together a little bit upwards to give a stronger dipole. So that makes water be a polar molecule, which explains a lot of things that water does. Before we go to the next page, look at this concept check down here. Can you guess which of these is polar and which of these is nonpolar? This one is nonpolar. That one is polar. Now can you figure out why that one's nonpolar and that one's polar? Well, these fluorines are all going to have the same electronegativity. These hydrogen, the hydrogen and the fluorine right here, they're not going to have the same electronegativity. So there's going to be a net dipole pointing to the right up here. You wouldn't have to know that direction. I'm not going to ask you about that. But just the fact that this and this are different and it's not a symmetrical molecule pretty much tips you off that that's going to be polar. And because this one's symmetrical, that's nonpolar. One of the weird behaviors of water, which I think we talked about in the previous chapter, is that when you freeze it, when you freeze the liquid water, it takes up more room, which is completely opposite from what almost every other liquid does. Most liquids, when you freeze them, it takes up less room. But you may have experienced this, like if you put a Coke bottle or a water bottle in the freezer or Powerade or something, and it's all the way full. You come back later when it's completely frozen, the cap's going to be busted off because the solid form of water takes up more space than the liquid form of water. And that's a really weird behavior. Most things don't do that. The reason that happens is because below about 4 Celsius, the random thermal vibration of the molecules is so low that these crystals, little crystal structures of molecules can form where the negative side of the oxygen right here is attracted to the positive hydrogen, negative oxygen, positive hydrogen, negative oxygen, positive hydrogen, negative, and so you see it forms a little ring, and that just happens throughout the whole structure. So you've got all these little voids where they previously didn't, like there's no molecule in here. Previously, when the thermal energy of the water was high enough and the vibrations of the molecules stopped these rings from forming, that space was taken up by another molecule. But now, because they're arranging themselves in these little rings, water is more like a crystal structure because of these repeating rings, and it takes up more space. That would not happen if water was not a polar molecule. If you've ever, you could try this at home if you ever cook some bacon or anything with grease. Pour that grease, let it cool off. You don't ever pour hot grease in water. That's a great way to flash boil some water and hurt yourself. Don't do that. But fill your sink up with some water. Let the grease cool off so that you could touch it. Then pour it in the water. You're going to see that you can't mix it very well at all. You're not going to mix up the oil and the water. And the reason that they don't mix up very well is because they repel each other, because water molecules are so attracted to themselves. Water molecules are so attracted to themselves because of their polarity that they pull themselves together. The non-polar oil molecules are excluded from that and left to stay by themselves. And being less dense than water, oil floats on. Grease from cooking food is made up of a lot of different kind of oils. I mean, it's not like the oil you pump out of the ground, but it has some of the same properties. Being less dense than water, oil floats on the surface where it poses a greater... Okay, yeah, so I'm not talking about the birds and wildlife in your sink, but if you do that and then you throw some Dawn, put some drops of Dawn cooking oil, Dawn soap in the sink, you'll see some crazy stuff happen. Things like when the soap drop hits the sink, everything just flies apart. Let me see if I can find a video. Okay, I found a video. It's a little hard to see because it's kind of dark, but it starts out with sort of greasy water, and then a drop of Dawn is put in, and you see that everything just flies apart from it. That's because of the way that dish soap works. Dish soap is extremely polar, so that it can just tear apart oils that are on things. And when the dish soap hits the surface of the water, everything just flies away from it. It's pretty crazy. Do try that at home, but remember, let the cooking oil or grease cool down first. All right, moving on. Here are the three ways that that matter really is held together. That trees, metals, well, actually not metals, metallic bond is not in here, but bulk matter is made up of molecules being attracted to other molecules. The strongest way that a molecule can be attracted to another molecule is ionic. That's the strongest. That occurs when an ion is attracted to a molecule with a dipole. The next strongest way that a molecule could be attracted to another molecule is with one dipole being attracted to another dipole, or a polar molecule being attracted to another polar molecule. That's not as strong as an ion attracted to a dipole, but it's stronger than a dipole attracted to an induced dipole. And induced dipole, induced sort of means to cause, to something that has been sort of created where it wasn't before. This occurs when a polar molecule causes a normally non-polar molecule to become slightly polar. It's like if you bring it's kind of like if you hold a magnet next to a paperclip for long enough, that paperclip kind of becomes magnetic itself. It's not a great analogy, but it's induced. It wasn't a permanent magnet before. Now it is, and it'll wear off eventually. So, some notes about ion-dipole interactions. This is when an ionic substance meets a polar substance. An ion interacting with a polar molecule is not as strong as an ionic bond itself, but it's stronger than the others. If any polar molecules surround a substance which is ionic, it could begin to pull it apart. So this is actually how water dissolves salt. Salt is ionic. If you throw a chunk of salt in water and just leave it, stirring it will make it happen faster, but if you just leave the salt in the water, it will dissolve because the water molecules are all polar. So here is the diagram down here, shows you this polar molecule, the positive side of it pulls on the negative ion, the chlorine, and the positive oxygen in the water molecule, the negative oxygen pulls on the positive sodium, and this is happening all over the salt, so it gets pulled apart. This is just a diagram showing a larger chunk, water molecules pulling away piece by piece. The next strongest interaction for molecules is dipole-dipole. So if two polar water molecules meet each other, that is not as strong as ion-dipole, but it is stronger than dipole-induced dipole. This occurs when two polar molecules exert forces on each other. One unusually strong way that this happens is called a hydrogen bond, which is kind of a big deal later in chemistry. Hydrogen bonds have a lot to do with organic chemistry. A hydrogen bond is the result of hydrogen atoms being covalently bonded to very electronegative atoms. So oxygen is pretty electronegative, meaning that its electronegativity is kind of high. When that happens, it causes a large dipole, and so hydrogen bonds can be stronger than other dipole-dipole bonds. Alright, finally you got dipole-induced dipole. This is like if you have an oxygen molecule by itself, it's not polar. But if it meets a really polar molecule like water, it can kind of induce or cause the oxygen molecule to become somewhat polar. Like, if oxygen approaches it, the oxygen from the water molecule is so negative that it can push some of the electrons to the other side, so they're over here more, and then this side's kind of positive, that side's kind of negative. But now it's like it's polar, so there's an attraction where there wasn't one before. It is the dipole-induced dipole interaction which holds oxygen molecules dissolved in water, which is what allows fish to breathe. So like pure water is just H2O molecules, but most water that you encounter is not pure water, especially in the sea. Like seas and oceans have varying levels of oxygen in them, but the oxygen is there. It's in the water, trapped. It's an oxygen molecule. O. It's not like when a fish breathes, it doesn't take the oxygen out of the water molecule. It's not dissolving, it's not like breaking apart the bonds in a water molecule. That's not the oxygen that the fish breathes. The fish breathes oxygen molecules that have become trapped in the water because of this induced dipole interaction. And I think that's it. Have a good day.
Disheveled.